ever stop to think about how the internet actually works? I mean, really works? In this explainer, we're going to pull back the curtain on its unsung hero, the router. We're going to find out exactly how this little box makes billions of lightning-fast decisions to get your data exactly where it needs to go.
Seriously, think about it for a second. You click on a link, and in what feels like an instant, a website from halfway across the planet just, poof, appears. How is that even possible? Well, it might feel like magic, but it's really just a masterpiece of high speed and surprisingly simple logic.
And the secret to all of this is the router. The best way to think about a router is like a traffic cop standing at the busiest intersection of the internet. It's its job to look at every single piece of your data and tell it exactly which way to go to avoid traffic jams and get to its destination as fast as possible. So at its core, a router's job really just boils down to two things. First up is path determination. It looks at its map of the entire internet and figures out the absolute best route for the data to take. And second, there's packet forwarding. Once it's picked that path, it physically sends the data packet on its way. That's it. Determine the path, forward the packet. Simple as that.
Okay, so how does it build that map in the first place? A router isn't born knowing the layout of the entire internet, right? It has to learn. And this map it builds is called a routing table, and it's basically the router's brain. So let's dig into how it actually gets filled up.
There are really three main ways a router learns. First, it automatically knows about its immediate neighbors. The networks it's physically plugged right into. Second, a network administrator can give it specific, handwritten directions, and we call those static routes. And third, and this is where it gets really powerful, it can talk to other routers and share information, dynamically learning about the network's layout through what are called dynamic routing protocols.
And this really shows you the two competing philosophies here. Static routing is kind of like having a printed map. It's simple, it's predictable, and it doesn't change, which makes it perfect for smaller, stable networks. Dynamic routing, on the other hand, is like a live GPS app on your phone. It's constantly updating, adapting to traffic and network changes in real time, which is absolutely essential for a massive, complex, ever-changing network like the internet.
So let's say a router has multiple possible paths in its map to get to the same destination. How does it choose just one? This is where things get really, really clever. It uses a single, incredibly powerful rule to make every single decision, and this one rule is the secret to its unbelievable speed. It's called the longest match rule, and here's how it works. The router looks at a packet's destination IP address and compares it to all the routes in its table. The route that matches that destination address for the longest stretch of numbers, reading from left to right, wins. Every single time. It's not about finding the shortest physical path. It's about finding the most specific address match. This rule is the reason the internet can even exist at its scale. It's a lightning-fast, crystal-clear way to make a decision with zero ambiguity.
Okay, so let's walk through this thought process step by step. First, a packet arrives at the router. Then, the router immediately pulls up its routing table, its map. Next, it finds all the routes that could possibly work. And then, it applies the longest match rule and picks the single most specific one. And finally, boom, it forwards the packet on its way. This exact process happens billions of times a second all over the world. Check out this example. It makes it super clear. So a packet needs to get to the address 172.16.0.10. The router looks at its table and finds three potential routes that all seem to match. Now that number after the slash, the prefix length, tells the router how specific the match is. The first route matches the first 12 bits of the address. The second one matches 18. But look at that last one. It matches a full 26 bits. Since 26 is the biggest number, it's the longest, most specific match. That's our winner, and that's the path the packet takes, no question.
Now, the longest match rule is all automatic, right? It's the router's built-in logic. But what if you, as the network administrator, want to force the router to take a specific path, no matter what? Well, that's where those manually configured static routes we talked about come into play. They let you write your own rules for the network.
Okay, so we know what happens when there are a bunch of matches. But what about the opposite scenario? What happens if a packet shows up and it's trying to get to a place the router has never even heard of? If there's no specific match in its rulebook, does it just give up? Does it just drop the packet? Not always. It can use a safety net, and it's got a great name, the Gateway of Last Resort. This is basically a default instruction that says, look, if you are completely lost and have absolutely no specific directions, just send the packet this way. It's the router's last-ditch effort to get the data where it needs to go. And this is what that ultimate match-anything route looks like. For IPv4, it's all zeros.
And you see that /0? That literally means 0 bits need to match. It's the shortest possible match, so by definition, it's only going to get used if nothing more specific can be found. It is the ultimate catch-all.
So we know how a router chooses a path. We know what it does when it gets lost. But what about building a network that can handle problems? What happens if that best path, the one it always chooses, suddenly goes down? Well, that's when you need a good backup plan.
And for that, we can create what's called a floating static route. The best way to think of this is like a detour that's always available, but it's completely ignored as long as the main highway is open. The second that main path fails, this backup route instantly activates and starts handling all the traffic.
Which leads to the obvious question, right? How does the router know which is which? It's got 2 routes to the exact same place. How does it know to prefer one path and only use the other one in case of an emergency?
The answer is a really simple but powerful concept called administrative distance, or AD for short. Just think of it as a trust score on a scale from 0 to 255. And the rule is dead simple. The router will always trust the route with a lower number. Lower is better. By default, a normal static route that you configure has an administrative distance of 1. That's a very low number, which means the router considers it highly trustworthy. So this becomes its go-to primary choice. So to create our backup, all we do is configure a second route to that same destination, but this time we manually give it a higher administrative distance, something like 5. Now the router sees 2 paths, one with a trust score of 1 and another with a score of 5. It will always use the route with the AD of 1 until it disappears from the network. Only then will it even consider using the backup route.
So let's put it all together. A router's thinking is really just governed by 2 simple but powerful rules. First, always pick the most specific path, thanks to the longest match rule. And second, always trust the path with the lowest administrative distance. By understanding these rules, network administrators can build a network that is both incredibly smart and incredibly resilient.
And all of this leaves us with a really fascinating question to think about. When you're designing a network, where do you draw the line? How much should you leave to the automatic, adaptive logic of dynamic protocols versus how much do you want to keep under the direct, manual control of an administrator? There's really no single right answer, and that fundamental trade-off is at the very heart of all modern network design.